So this is where we'll actually go into another notebook here with activation functions and kind of say like what different parts are. So kind of mentioning a little bit is activation functions. There are different things we can do, but the main goal of our activation functions is going to be creating nonlinear relationships. So remember right now, all we're doing is basically doing linear relationships. You might be doing many of them, but if you never add nonlinear parts in there, it's never really going to have the complexity that you want. So that's where activation functions come in. So I'm going to go to this notebook now. I should close these guys. Okay, so I'm just going to quickly go through this more in section 45. But I think it's important to kind of see how these interact together. So remember, our activation function is just going to take in whatever value from linear combination and transform it. And this will actually play a big role in backpropagation, which we'll talk about in a second. But basically, the idea there is going to take some number. So for example, if you have like 10 million, it's like, well, you don't want to have 10 million all the way through. We'll usually shrink that down in some way. And there's a few ways we can do this. So I don't know, I have this one first, to be quite honest. Okay, we'll ignore that. The first one that we're going to use is something called sigmoid. Oops. And so sigmoid is like the classic, one. This is very similar to a logistic regression. So if I actually write this out, you can see it. Is our sigmoid here is in blue. I'm sorry, not blue, in red here. I have that right? Yeah, our sigmoid is in red here. And basically, whatever value you have on this x-axis, the y-axis is going to be between 0 and 1. So there's some really great advantages of this, is that basically it's intuitive for classification. It's like for classification, it's either a cat or it's not a cat, right? Is it blue or is it not blue? 0 and 1. So this makes it really nice and easy. And basically the larger this value is, right, the closer it is to 100%, it's going to be like, oh, that's definitely a cat or that's definitely blue. Note that for logistics, a sigmoid, is that it's never going to reach 100%, even if it's like 10 billion, right? It's never going to be exactly 1. It's going to be close, but never exactly. And that kind of makes sense in our probabilistic world. If you're getting closer to 0, it doesn't really know. It's got a 50-50 chance. So this point right here will be 50. And what would be nice, though, in here is that when backpropagation, we'll actually use gradient descent, and it's going to depend on this this derivative here. And so it turns out, like, if you're over here, you're like, okay, like don't move the value very far because basically the gradient's very small over like very large values. So it's not going to budge very much. But if the value is closer to over here, right, it's going to move it closer and closer. It's going to move it more significantly. So this blue here is representing the derivative. So you can think of like the derivative in this case is like how much should you nudge it if it's like the value is in this case, like, let's say the value is like 2.5. It's like we'll nudge it a little bit in the positive direction. Or if it's at this top right here, it's not going to move at all because it's basically unsure to go either direction. But if it's a little uncertain, it's like, oh yeah, definitely move that over to, no, or definitely move that over to yes. So that's where the derivative kind of plays in a role. Okay. So some of the advantages, even though it's really common, is that it's not super efficient at training. And basically that's come of the derivative, is that if you have something that's like really, really certain, it's not going to move very much. And so this derivative is actually kind of small, and you have this problem called the vanishing gradient problem. Basically, this gradient's not going to improve your machine learning algorithm's only going to do a little bit of a nudge. It's like, well, it's going to be more careful, essentially. So one, improvement from this is through hyperbolic tangent. So usually tangent h. And so what this looks like, this is the actual, the formula for it, is we'll go from -1 to 1. But what's the real nice thing about it is that it's going to have a steeper gradient. So if you notice this gradient in blue, this gradient is going to be, in this case, you can see it's much steeper, goes up to 1 here. And you can even see it from the red line, which is the actual function itself, is that it's definitely steeper than that original sigmoid here. Okay, and that will allow us to basically have more efficient training and stuff like that because of that steeper gradient. However, the same problem comes here is that it suffers from the gradient problem, is that if you're over on this part right here, it's not going to change very much. The gradient's nearly 0. You can see here. It's not exactly 0, but it's pretty damn close. Okay. All right. So most modern systems now use something called ReLU. So this is called a rectified linear unit. And one thing you'll notice right away is that it's not a function in the same way. It's a piecewise function. Basically, if the x value is less than 0, meaning that it's not doing a good job, or it should be the opposite of whatever it's classifying, it's just going to set it to 0. And then if it's doing a good job, it's going to just repeat that value. So what this looks like this guy. So in red here, again, it's the actual ReLU function. And you can see basically it's 0 when it's negative, and then it's just the value if it's positive. So what's really nice about this is that this actually trains very quickly, because basically if you have a neuron that says, hey, this value is super important, it's going to modify that value and bump it up a lot, right? So this is going to bump it up consistently, I should say, because the derivative is 1. But what's nice about that is that it's consistently going to move it up, versus our derivative from before for the sigmoid and hyperbolic tangent. It's going to kind of like that derivative is going to kind of go away slowly. So it turns out ReLU is actually really great at training. It's really efficient. It's pretty quick and everything like that. It also specifies a more positive activation. So this kind of makes sense. If you have a neuron that's doing a really good job of predicting things, like if you have like one feature or some combination of features and does a really great job of predicting something, you want to say, hey, this neuron's important. Let's bump it up more. And so that's what allows, ReLU allows to backpropagation and say, hey, this is really important. One disadvantage you can see is that if it's negative, if it's not doing a good job, it's doing the opposite, you kind of get like this 0 part. And basically that means like if something's like, oh, this is like the opposite of it, predicting it, right? It's like minus 10,000. Well, the problem is that's going to be the same thing. It's like, oh, it's all right, like minus 1. It's going to still give a gradient of 0. So it's not really going to adjust it too much. So you would think this might be like a really big like disadvantage, but it turns out in practice, by optimizing towards, saying what's positive, this actually does a pretty great job. But there is one in particular that has kind of like improvement, which is called the leaky ReLU, which you'll see here is basically the same idea as the ReLU, except we basically have, instead of just 0 for if it's negative, you have it by some factor, C, and the C part will basically make it a little bit negative. So what this looks like in practice, we can graph it out, is basically the ReLU's here. We can see basically there's a little bit of like leakiness, essentially. There's a little bit more negativity. So that way, if it is really negative, it's like, oh wait, that's really negative. We should kind of keep bumping it down towards that direction. And that way the gradient is just slightly under 0. So again, another way you can do things. Some disadvantages of this is that it's a little more complex, because when x is negative, instead of just setting it to 0, it means it has to figure out that specific number, which can slow down some things, but sometimes this can actually help with training. So just a trade-off. It just depends on the situation. Okay. So those are different activation functions. And remember, our different activation functions are really at that point when we do it with the linear combination, we combine them together and we say, all right, should you move in the positive direction or should you move in the negative direction? Okay. Any overall questions for activation? I'm assuming you guys have seen a little bit of this already in section 44 or maybe 45. Okay. Cool. How are we doing overall? Thumbs up, thumbs down, sideways? All right, I saw a lot of quick thumbs up, so I'm thinking that's a good thing. All right, cool. So